But let me first tell you what this session is going to be about in a little bit more detail and maybe give you some hints when you can use this information. Because probably at a first glance, this sounds fairly abstract, right? Distributed gradient descent, gradient accumulation. Will I ever need this in my work? And I'll try to convince you that you should know about this stuff. If you're definitely if you're a machine learning engineer, if you're a data scientist or data practitioner, you need to be aware of the concepts in this notebook. So what are those concepts? First of all, in terms of the gradient descent, I'll talk about this idea of gradient accumulation. Now, if you've seen my automatic differentiation video before today, you've had some exposure to the ideas behind gradient accumulation. So I'm not going to spend too much time on that, but I encourage you to check out the automatic differentiation video if this is just brand new to you. So how are we going to use gradient accumulation? Gradient accumulation is going to be the fundamental concept in scaling out the gradient descent algorithm, right? The algorithm to train deep neural networks. And I'll show you the role that this gradient accumulation plays in both what are known as parameter server-based distributed deep learning training models and what are known as ring-based distributed training models. And in particular, Horovod is a special type of a ring-based approach to distributing gradient descent. And specifically, I'll give you quite a bit of detail around these two key phases that exist in Horovod called reduce scatter and all gather, or sometimes it's called reduce all phases. And you'll see the role that they play in really making gradient descent efficient in distributed environments. Okay, so why should you care about all this stuff? Now, if you are in a role where you're working with a decision maker, so maybe you're a lead machine learning engineer on your project, your team or organization, maybe you're an architect, helping somebody decide whether they should buy or build their deep learning platform, I definitely think you should know about the contents of this session and this notebook. So if you're influencing buy versus build decisions, a lot of very important ideas here that you need to be aware of. Or even if you're a practitioner and if you want to make sure that your deep learning models can scale out and also scale out to out-of-memory data sets, right? Data sets that don't fit into a memory of a single computer, single server, you should be aware of the concepts in this notebook. And even if you are just troubleshooting deep learning, researching deep learning, I think there are a lot of ideas here that can give you some direction and make you a better practitioner. And also, if you are at the cutting edge of machine learning, maybe you're academia and you're interested in topics like federated deep learning, if you're interested in doing deep learning at the edge of a cloud, on IoT devices, any kind of bandwidth constrained environments, you definitely should know about the kind of algorithms that I explained in this notebook. So without further ado, let me go ahead and start sharing some code. This first code cell that you're looking at right now, you can see that I just put it in focus. Simply does the basics. So you'll notice I'm initializing the standard toolkit, very familiar to anybody who is a data scientist, machine learning practitioner in Python, your NumPy, Pandas, Matplotlib for visualizations, and PyTorch, of course, which is what you'll be using. And also I am setting the pseudo-random number seed generator. So what I just did right now was to hit Shift-Enter, which executes this cell. And if you're trying to follow along, you'll see a very similar kind of pop-up. So just don't worry about this. You probably already know about the fact that since this is loaded from GitHub, it complains that the notebook is not authored by Google. Well, I'm going to hit run anyway because this notebook doesn't do anything with your Google account. So what does this cell do? After importing the prereq libraries, setting the pseudo-random number generator for both PyTorch and NumPy, this simply spits out the versions of the various prerequisite libraries that I'm using, just for reference, so you know exactly what I'm working with. In particular, just notice that I'm using version 1.7 of PyTorch. This is the CUDA enabled, right? So this can run on GPUs or scale PyTorch models to GPUs. But in this session, you're actually not going to be doing anything with GPUs at all. Just be aware that it's a possibility. Okay, So how am I going to introduce all these ideas around gradient descent, gradient accumulation, and more? This session is not about making sophisticated deep learning models. In fact, I intentionally picked the minimal example that can help us explain Horovod so that we don't get distracted into the machine learning side of things or data science side of things, and can instead focus on Horovod and gradient descent themselves. So from the model standpoint, you can see that this is just a workhorse of data science. This is linear regression. In particular, it's multivariate linear regression. You'll see why I picked a multivariate option a little bit later in the notebook. But notice that the way I'm setting up this multivariate linear regression model is that I'm pre-creating my own training data set. So I'm actually going to generate a synthetic training data set. And again, just because I don't want to focus on the model in this session, instead I want to focus on how to train models in a distributed setting. And in this case, notice that the data set has 1,000 examples and it has 4 features. If you prefer, you can think of these as independent variables for the multivariate linear regression. So let's go ahead and initialize this code cell. So this makes sure that you have your constants for generating the data. And I see I'm getting a few hellos there in the chat. So let me just say hello, everyone. Again, questions welcome as always. But the next thing I'm going to do here in the cell is to actually create a sample data set. And in particular, I'll use the NumPy library to create this data set. So there's a hint here that I can use this multivariate normal function. And even if you are experienced with NumPy, you may not have seen this in the past. So let me explain what is this about. So I'm going to create this ND array, as they're called in NumPy. And this particular ND array is going to consist of pseudo-random numbers. And this multivariate normal function is actually going to give me 4 different columns worth of data. Remember, you have 4 features in this multivariate linear regression. So I'll set up 4 different columns, and each column will be its own, it will be sampled from its own normal distribution. Think bell-shaped curve. The only thing that's going to be different between them is that I'll actually set this up so that each column will have a different mean. So remember that in NumPy you have this A range, so I'll have values like 0, 1, 2, and 3. So this will make sure that each column will have a mean of 0, then 1, 2, and so forth. And the other interesting thing that I'm going to set up is that I'll make sure that all the values in the rows of this sample training data set are uncorrelated. So to do that, I'll make sure that I set up this identity matrix as the argument to the multivariate normal. And if you're a little hazy on what the identity matrix is in linear algebra, I'll just come back in a few cells and actually illustrate this to you exactly what it looks like. So let's use this identity matrix to specify the correlations between the columns in this training data set. And then finally, I have to specify how many different rows of data I want to have in this X NumPy ND array. And this specifies that I want to have 1,000 rows, right? We agreed the training data set is 1,000 rows. And in a nutshell, this is what it looks like, but let me give you a visual perspective so it's easier to follow. So what I can do is use matplotlib and actually plot one of the columns from the from XNumPy. So let's go ahead and plot that. And you can see that if I plot it, it kind of looks like standard normal distribution, but let me actually increase the number of bins so you can get a better resolution into what's going on with the data. And now you can see that the first column, right, the column index 0 is roughly normally distributed with a mean at 0, as I discussed. And in fact, if you look at the other column, so let's pick the last column was index 3. I can plot it on the same plot, and as I pointed out, this one is going to be normally distributed as well. If you're wondering why I'm using these standard normal distributions, remember that multivariate linear regression really works well when you have these independent variables that are normally distributed, and that's really what I'm after. So I'm not trying to set up a complex data set or a complex model. Instead, I'll focus more on having an efficient solution that works in a cloud-based environment. So this gives you a little bit of a perspective into the columns themselves. And what I wanted to point out is that the columns also have a very special relationship. So if I actually go ahead and create a data frame from this X NumPy and show you the correlations across these columns. So this is the pandas data frame that shows the correlations. Notice that the identity matrix that specified the correlations did its job. So as you know, from the identity matrix, you have ones along this diagonal, and everything else should be 0 in the identity matrix. And this is roughly what you're seeing in this case. Of course, since we're sampling the random values from that pseudo-random number generator, it's trying its best to get the correlations. For example, here, the correlations between column 0 and column 1 to be 0. It's not exactly 0, but it's close enough, right? As they say, close enough for government work. So let's go ahead and start building up a little bit of a data set in PyTorch from this data. Now in PyTorch, what I can actually do is create this X-train tensor. So as you recall, in PyTorch, you can create tensors, and you can create them using NumPy ND arrays. And that's exactly what I'm going to do here. So I'm passing in this NumPy ND array. And also what I'd like to do is specify the data type. So let's actually be specific, and let's say that this should be 64-bit wide floating point value. And also what I'd like to do, and this is just a general best practice that I find works well when you're working with PyTorch, is to build in, to have some runtime checks for yourself that the tensors you create actually have expected sizes. So what I'll do is actually reshape this to the training data set size by feature size, right? So I expect this to have 1,000 rows and 4 columns in each row. And this is just to make sure that if something goes wrong in the code, I'll get a runtime error, and I'll know where the error is coming from, instead of trying to chase it down after a bunch of other operations. So let's take a quick look. And now you can see that this is pretty much what you would have expected from the original data set, right? Same values here that used to be NumPy. And here they're simply converted into a PyTorch tensor. Now, if you check out my book, I talk about the fact that the underlying memory in this server that's processing this data is actually shared. So we're sharing the memory across the NumPy ND array and the PyTorch tensor, but this is more of a technical topic. Just what you need to know from this is that this is an efficient way of creating a PyTorch tensor from the underlying NumPy data. Okay, so what's the result? Notice that now you have some training data. You have the independent variables or the features that you can use for the linear regression model. Now let's go ahead and actually set up the dependent variable. And what I'm going to do here is create the coefficients for the dependent variable. Think back to the definition of linear regression. You know that each independent variable is multiplied by some coefficient, and that's exactly what I'm doing here. And in fact, let me actually make this also explicit, and I'll specify this to be a 64-bit wide floating point number as well. So this is going to be the coefficient for column 0, column 1, and so forth. And at this point, you can actually go ahead and create your independent variable. So dependent variable. And let's do that. There are different ways you can do this. Of course, I'm sure you know you can take the X-train and do a matrix multiply coefficients, right? This would give you what you expect. But if you're not familiar with matrix multiply, just in case, think of it in terms of the following NumPy operations. That's the same thing as taking every row of X-train, multiplying that by coefficients, right? Coefficients. Actually, copy and paste it, otherwise I'll make too many typing errors. So multiply every row by these coefficients, and then simply sum them up, right? And the sum has to happen along the horizontal axis, so I'll specify it as x1. So that's exactly what happened in this case. And in fact, what I can do is make sure that this has the expected shape. So for example, I can say that this should be X-train, reshape. Let's reshape it as training dataset size. And this way, you know exactly what the shape is after the Y train is produced. Now, as I pointed this out just a few moments ago, the X train and the Y train tensors are simply there to help you set up this linear regression problem. And just to understand the problem itself, I created this visualization. Now remember, I'm trying to visualize 4 dimensions of the features and a single dimension of that dependent variable. So let me parse out exactly what's going on in this diagram. But I think just with your human pattern recognition, you can see the trend or the pattern that exists in this data. Notice that if we take the first spatial dimension, it's this one right here that I'm pointing out with a cursor, notice that as you move along these dimensions towards higher and higher values, the dependent variable, which is marked here with the color of these data points, becomes higher, or the color changes towards yellow, which corresponds to the higher values of colors on the right. Whereas as you go in the opposite direction for the first spatial dimension and also other spatial dimensions as well, you get closer to a 0. And you might be wondering, where's that fourth column? Well, the fourth column from the data set, that fourth independent variable, is visualized here using the diameter of the individual data points. But you can see that even if you increase the first 3 dimensions, the diameter doesn't really make much of a difference, right? That last feature, that last column from the data set is not having a lot of effect on the dependent variable. And why? And that's simply because, remember, the coefficient was 5 for the first column, this one right here, the spatial column along this axis marked x sub 0. And the last dimension that had to do with the diameter of the data points is simply multiplied by 1. So it's not as important in creating the value for the dependent variable. So hopefully this makes sense as a data set. And what I want to point out is that the problem that you'll be working on in this entire notebook is solving the classic linear regression. In other words, giving these data points, right? Given information about the spatial and the diameter dimension of these data points, you want to recover the coefficients, okay? And what I'll do in this notebook is explain how you can use classical gradient descent and then make that gradient descent efficient in distributed environments, like the kind of environments you can encounter in cloud or any distributed environment where you have multiple servers internetworked together. You'll figure out how to make that gradient descent efficient so it runs faster, so it can run with limited amount of memory and limited amount of bandwidth. So how do you do that? Well, first, let's explain how you would solve this using just a classical, ordinary vanilla gradient descent. So how do you do that? As you know, in deep learning, the first thing you do is set up a model. So in this case, the model is super simple. And I'll start by initializing just a few random values for the model, parameters. And these random values are going to be in the shape of features by 1, right? So this is a single columned matrix or single columned matrix of values. And there are going to be 4 rows in this matrix. If you prefer to visualize this, let me go ahead and type this in this way. And now you can see that this is NumPy ND array in exactly the shape that I just pointed out. There's a single column and every row has a model parameter. The model parameter is initialized using just a Gaussian distribution, right? This is the standard normal distribution, mean at 0, standard deviation of 1. Of course, if you come in from a deep learning background, I'm sure you know there are many more complex initialization schemes, like you can use K-Ming, Xavier initialization. There are others that are available in PyTorch, but the cool thing is, in this case, it's not going to matter. So since we're working with such a simple model, right, intentionally a simple model, the initialization scheme is not going to be important, but I encourage you to try something else if you prefer, like K-Ming from PyTorch. Now, why did I initialize these values as a NumPy ND array? The reason is simple. I'll want to reuse these same parameter values, these model parameters, over and over again in the notebook So I'd like to be able to go back and just pull that data from the original array. So let's put this in the w_numpy and then keep referring to it over and over again. So now that you have the data or the values for the model parameters, let's actually set up the model as a PyTorch tensor. And to do that, again, very straightforward. Let's create this W tensor to represent the weights tensor of the model. And this is just going to be PyTorch tensor with the w_numpy. And I'm going to have to set up the requires grad for this to be true. So if you're not sure what requires grad true does, I encourage you to open my automatic differentiation notebook. It's linked from this notebook as well, or just search automatic differentiation PyTorch on YouTube. My name's going to come up there. Definitely check out that that video to learn more about requires grad true, how it works behind the scenes. But in a nutshell, what's going on is that when I enable requires grad true, this allows me to actually compute the gradients, the derivatives of these individual weights with respect to the loss function or the cost function of the model that you're going to build. And in particular, you're going to use the mean squared error loss function, and you're going to be able to calculate the gradients of this model with respect to the mean squared error of the model and the data, which is really what deep learning is about. So let's go ahead and set up the rest of the components that you need for doing gradient descent. The first component that I'll set up is this forward method. So the way that the forward method is going to work is that I'll take the model, W, and the data, marked here as X, and recall that this is the features or the independent variables of the model, if you prefer to think of them that way. And really, the only thing that the forward method needs to do is to return the product of the input data, right, these features, and the weight, lowercase w. And the way that this should be returned, right, if you think about the results, this should have the same shape as the shape of the input data along the first dimension. So let me parse this out a little bit and explain what this means. So remember that the x is the tensor of features. So when I multiply that tensor by features, I expect that I'll get back another tensor that has as many training examples or as many outputs as there were training examples in X. So specifically in our case, X has 1,000 training examples. So this makes sure that the result of this matrix multiplication also has 1,000 training examples. And again, I'm just doing this as a sanity check to prevent bugs or detect bugs if they do happen somewhere in the code. So that's the forward function. And as you would expect, you can now take the model that was just initialized, pass in xtrain, and get back some estimates for the dependent variable, in this case for y, based on this model. And of course, right now, the model is just a collection of randomly generated values. But that's what deep learning is all about, right? So you have a model, you make an initial guess, and then you improve the model over time so that the estimates, the guesses, become closer to the target, to what your specified value for the target is, in order to minimize the loss function. Well, in this case, the loss function is the mean square error for linear regression. So how is this going to work? Well, this is just your standard mean squared error. Let's compute the error first. The error is simply the difference between the estimated values for y and the actual or the target values for y. And then what you want to return is the mean squared error, right? So here we have the error. Let's go ahead and square it and then return the mean of that squared error. And this allows you to actually go ahead and compute that mean squared error. So let's go ahead and pass in the initial set of estimates, the actual or the target values, and find out what that loss is. And in this case, you can see that loss came in at about 122. So very deep learning 101, right? So hopefully much of this is a review, because now I'll actually solve the multivariate linear regression using just ordinary gradient descent. If you're wondering why am I linking to Wikipedia here, is that I want to emphasize that this gradient descent is not stochastic and it's not mini batch gradient descent. This is just your plain vanilla ordinary gradient descent that processes the entire epoch worth of data for every iteration of gradient descent. So how would you do this? Let's actually go ahead and set this up. So let's do for epoch in range epochs. So if you're wondering where this number of 400 epochs come from, I can tell you that I picked it to make the results that are returned by the algorithm more interesting. So what more interesting means, I'll explain in a second, but basically we'll get about halfway to solving the problem, and this will make it more interesting for us to follow some of the later examples in the notebook. So let's do 400 epochs of gradient descent. Again, just as you've seen moments ago, let's do a forward pass of gradient descent using the model and the training data set. Let's go ahead and compute the loss using mean squared error that you just created. So the mean squared error will take the estimated y values and the y values from the training data set. And now you can actually compute the backward pass or perform back propagation to fill in the gradient values. So if you think back as to why I've set up requires grad to be true, well, it's so that I can actually perform this loss.backward. Which means that now I can do a couple of things. One is that I can perform a step of gradient descent by changing the weights in the direction opposite of the gradient, right? And I'll use w.grad scaled by the learning rate right here. Again, why that value? You'll see in a moment to make the values more interesting. And then, as you know from my my video on automatic differentiation, you want to clear out the gradients to prevent them from accumulating. So at this point, you might be wondering, why am I clearing out accumulated gradients if this session is all about gradient accumulation? Well, just hang on, I'll explain in a moment. But now, if I run this simple implementation, notice that after 400 epochs, right, these 400 passes through the entire training data set, it recovered the coefficients from the data fairly well. So it's not exact, but it's about 5, 3, 2, and 1, as we expected. And this is what I meant by having these values be more interesting. So I intentionally picked the number of epochs and the learning rate so that I don't get exactly the coefficients that were specified when generating the data. And that's because in just a moment, I'll re-implement this gradient descent using a slightly different approach, and I'll get the same values. So let's work on that. But in a nutshell, if I run this again, right, another 400 epochs, you'll see that technically this gradient descent approach to solving multivariate linear regression can recover effectively the exact coefficients. But let's use our original values for W and continue from here. So we're doing great on time, and what I'd like to do now is actually shift gears and start talking about new topics that I introduced in this notebook and that I explained in my book. So if you've followed along up until this point, hopefully virtually everything has been a review. If something doesn't really feel like a review, I encourage you to go back to the link right here, the link on automatic differentiation explained. It's another YouTube video that I've done. It gets into the details of gradient descent with automatic differentiations, gradients in PyTorch, and more. So if you feel like maybe you're lacking the background, definitely check this out. But if you're still with me, if you're comfortable with the ideas of gradient descent that I just introduced, what I'm going to do is shift gears and use the data set that was just created to demonstrate distributed gradient descent on the basis of gradient accumulation. So let's go back to where we left off, and it was right at this diagram right here. Gradient descent using gradient accumulation. So first of all, why should you care about this topic? One of the key reasons why this idea of gradient accumulation is important, or why it's important from the engineering point of view, is that this allows you to actually work with data sets that don't fit in memory. And if you follow machine learning, if you follow deep learning, I'm sure you know that the machine learning models that succeed in production are the ones that actually are able to scale to massive data sets. And here, this approach actually will allow you to scale to these massive data sets that don't fit into gigabytes or potentially terabytes of memory in your nodes. So how does this work? First, I have to introduce you to this idea of a shard of a training data set, or shard of a data set in general, and just highlight that this shard is not a batch, okay? I'm sure you have heard of this idea of mini batch gradient descent, and you may think that the shard and the batch are basically the same thing. They're not. And I'll explain the difference in just a moment. Think of a shard as just as a part of a data set, training data set in this case, that is guaranteed to fit in memory of whatever node you're using to run gradient descent. And just as an example, let's say for us, we want to only store 250 training examples in a shard. Of course, here in this notebook, I can store more in memory, but let's use this as an example, right? Let's use this as an idea for limiting the amount of memory that you need to process gradient descent. And the shards are actually shown here on the left-hand side of the diagram. So notice that I'm using Python slicing notation, and what this is saying is that if you take the first shard worth of training examples, the first 250 of them, you pass them through a model. So just like before, you have this PyTorch tensor of model parameters called W, and what you get back is some gradients, right? So you pass through the model, you perform loss.backwards, and what you get back in the model gradients are the gradients that are corresponding to the shard of data right here, right? So this 0, the sub-index that I'm using, indicates that this set of gradients shown by G actually matches the shard with the index 0. Now, and again, this is based on what I've covered in the automatic differentiation topic. What happens is that if you actually give a second shard worth of training examples to the same model, to the same model parameter tensors, what you'll get back after computing loss.backwards is actually accumulation of gradients. So what you'll get is effectively a sum of the gradients based on the second shard, right, index 1, the second shard worth of data, but the original gradient values are still going to be there. And in fact, this continues as you execute multiple of these sequential passes for shards of data. So then for the index 2 shard, you'll get gradients from index 2 all the way to 0. And then with the last shard, you'll actually accumulate all the gradients for all the shards that you've processed. But notice that you're doing the processing here sequentially, right? One shard at a time, which is fine because you can only store one of these shards worth of data in memory. So you can process this shard, then release memory for that shard, take the next shard worth of data, the next shard, and so forth. But ultimately, when you're done processing all these shards worth of data, you can actually take the next step, which is to update the model using the accumulated gradients and get back exactly the same result that you had with ordinary gradient descent, where you process the entire data set at once. So just to illustrate this point, let's actually go ahead and do this. Let's create this in-memory shard. As I said, I'll limit it to 250 training examples. And I'll reinitialize the model. Remember, this is the model tensor based on those original NumPy values. And the reason why I'll do this is to show you that I'll get back exactly those same interesting results that I got before. So let's go ahead and implement this kind of gradient descent using shards. So what does it mean to do this? Let's go ahead and first use these PyTorch utilities to wrap the original data set into something that can can be sharded, right? Can be split into partitions into parts. So I'll create this training data set using tensor dataset utility, and this will guarantee that I can get back the Y and the features. And then I'll create something called the training data loader. So this will be a data loader instance. Again, this is from PyTorch. And this will take the training data set. And here, there are a few things that might jump out at you. So in the original PyTorch, the data loader assumes that you're doing training in batches. That's not exactly what we're doing here. We're actually going to train on the entire epoch worth of data. But this data loader takes the initial data in this training data set and partitions it so that every iteration, or every time you make a call to the training data loader, you get back, in our case, 250 examples, but in general, the batch size of examples. So even though you see the batch size here, don't be distracted by this. We're not doing mini batch gradient descent. As you'll see, we are doing just regular gradient descent with the entire training data set. And with respect to shuffle false, actually, I'll just point this out that if you're running this in production, you definitely should use shuffle true. The reason why I disabled the shuffling of the data or reordering of the initial values from the data set is that so again, I get back consistent values and I can point you that I am getting the same values over and over again. So this will make the live stream a little bit easier to follow. You'll see that the results are the same regardless of the approach that I use. So this training data loader will partition the data for me, right? So here, I know the data is in memory, so I don't really have an out of memory condition, but I hope you'll indulge me for a moment. In practice, there are what are known as iteration style data sets in PyTorch, and those can process out of memory data. But in this case, for the example, let's just stick to the tensor data set. So how do you actually implement gradient descent using these techniques? Well, a few things. Let's go ahead and actually take these shards of data in training data loader. And I'll repeat this actually for epoch times. So let's do for epoch in range epochs. This will actually return the Y shard and X shard worth of data. And now what I can do is just the same gradient descent that you've seen moments ago. So I'll estimate the Y values using the forward method. So remember, this will take the W, but now I'll use just the shard worth of data instead of the entire data set. I'll compute the loss. So I'll do MSC and use the estimated values versus the Y shard values, right? The ones from the training data. Then I'll do loss backwards. And then I can technically do, well, let's do the gradient descent here and see what happens. So notice that if I do the implementation of gradient descent exactly like I did before, it will actually surprisingly work. It might be surprising to you, but let's go ahead and run this. So this is pretty much it. What I'll do is also add another code cell here to show you the coefficients. And this should immediately start scaring you. So notice that this worked. It gave me the perfect coefficients that I specified into multivariate linear regression. But remember, just moments ago, I said that I had some of these interesting values that I wanted to use that came out of original gradient descent. Let's get back to those interesting values. Let's see what they were. They were not exactly the coefficients, but close enough. So clearly now the behavior that I just shown you is not what you should have expected. So there's something different going on. What's different? There are actually two things that are different. One, remember that I said that you want to accumulate gradients as you go from processing one shard of data to the next. And what's happening in this implementation? Well, first of all, the gradients are cleared out, right? Every iteration of this inner for loop, the gradients are cleared out. So that shouldn't work. And then notice that for every shard, I'm actually updating the gradients. So if you're familiar with mini-batch gradient descent, your ears might perk up here and say, hey, this is mini-batch gradient descent. This shouldn't, you're not doing what you've just outlined in the graphic. What's going on? And you're exactly right. So what's happening now is that the way I'm updating the gradients actually corresponds to using mini-batch gradient descent with a batch of 250 training examples. That's not what I need to do. So how do I go back? How do I fix this? Well, in Python, it's surprisingly easy. Notice that I moved these two lines to be in the same scope as the outer for loop right here. And now you're going to process the 4 shards worth of training data set in this for loop. And only after that, you're going to perform a step of gradient descent right here. And then you're going to clear out the accumulated gradients. And whenever you call last.backward, the gradients that are computed, that existed in the model will still be there. So this accumulates the gradients until they're cleared out right here. Again, if this idea of gradient accumulation here does not make sense, I really encourage you to go back to that automatic differentiation video. But there's one more thing, but I'll show you that this technically works better, but this can surprisingly fail. Okay, so notice that it's still not giving you exactly the kind of results that you should expect. So why is that? Well, there's a very subtle issue here that I did not address. And I say it's subtle because it can come up if you make just a small, seemingly small change to the training shard size, right? I'm not using really the batches here. I'm changing the shards. And notice that if I'm using 10 training examples per shard, which you could say that's how much fits into memory, 1/100th of your initial data set, this stops working. So clearly something is going wrong. That's not what you want. So what's the problem? Well, here's the problem. Remember what this mean squared error function is doing? If you think about the behind the scenes implementation, this is taking the difference between the estimated values for y and what's there in the target values in this y dependent variable. It's squaring that difference and then summing up these squared values, right? It computes the sum of the squared differences. And then finally, it actually has to compute the mean of these squared differences. So what is used there for the mean? Well, it divides everything by in-memory shard size. So if you think about what's going on here, this is actually computing the squared error per training example in the shard, right? So this is a different unit than what you would expected from training on the entire training data set, right? When you're training on the entire training data set, the mean should be per example in the training data set. Well, luckily, this is easy to fix. This is just basic arithmetic. And how do you fix it? Well, just multiply this by 1 over memory size, shard size over training data set size. You would multiply this. Notice that now the shard size cancels out. Here it's in the numerator, here it's in the denominator. And then now you rescale these squared differences to be what you started with, which is the training data set size. And you can easily modify this. For example, if you were working with batches of data, instead of using the training data set size, this would be your batch size, right? So let's go ahead and keep this. Let's just use the original implementation of mean squared error. There we go. And let's rerun this. So let's actually rerun this using the original model parameter values and see what you get. So now, if you take a look at the result, these are exactly the same results that you've seen before, right? Exactly those same interesting values when you trained on the original epoch worth of data for 400 epochs. So this is how how this algorithm works in a nutshell. it's doing this kind of gradient accumulation. This has some advantages. This allows you to actually limit the amount of memory that you're using to process the training data sets with gradient descent, right? So technically, each one of these can be released from memory every time you complete a single iteration. So that's great. However, this actually is slower than the original implementation. Why? Well, it's because for every epoch, you have this inner for loop. And this inner for loop right now is sequential. But it doesn't have to be. Notice that everything here conceptually can be done completely in parallel. What if you had independent processes or maybe even independent nodes in the network that could do this kind of processing in parallel, then communicate their results somewhere to update the gradients and then update their model correspondingly? This would mean that everything here in this inner for loop can be done with nodes that have some limited amount of memory, and you can avoid having this overhead or the slowdown from sequential accumulation of the gradients. That's sort of an obvious idea, and this was in fact made popular by the first version of TensorFlow, some of the first versions of TensorFlow, the frameworks behind Google Cloud, what now is Google Cloud AI platform. And what I'm describing is what's known as a parameter server-based gradient descent. So this is a distributed version of gradient descent. It's distributed multi-node. And the idea here is precisely what I just described. So notice that these dashed lines outline the boundaries of workers. And these can be virtual servers, physical servers. You can think of them even as processes running on a CPU, on GPU, graphical processing unit. It doesn't matter. What matters here is that each one of these can work in parallel. And the important aspect of all of these is that each and every one of them have their own copies of the model parameters of its own model, marked here as W. So W is identical for each one of these workers, which means that all of them can get these independent partitions or shards of the original data set, process them, get the gradients, and then every worker will actually end up with its own separate copy of the gradients. Okay, so notice again, I'm using the subscript to map the shard back to its corresponding gradients. So this is fine, but then the question is, how do you actually update this model? Because as I said, the approach assumes that the models are identical on every worker. Otherwise, this is not going to operate correctly. Well, in this original approach, in this legacy approach, in addition to the workers, you also had this idea of parameter servers. And the parameter servers are responsible for aggregating the individual gradients. So in fact, after every worker computes its own gradient, it sends those gradients with an identifier of the model that it used to the parameter server. The parameter server is responsible for reducing these gradients, or in this case, adding these gradients together to get that accumulated gradient, right? The sum of those gradients, and then use those accumulated gradients to produce a new copy of the model, these new values for the model's tensor. So here the new model is shown as W prime. And then after that is done, the parameter server would send the updated model back to the workers so that they have an identical copy of the model on the workers, and the cycle repeats. Okay, so this is the legacy approach. I say it's legacy, you'll still be surprised how often it's used. So this seems like you have a single point of failure with the parameter server. So in some cases, the parameter server is distributed. You might have a cluster of these parameter servers for reliability. In some cases, you may see environments where the parameter server is running on the same physical hardware or virtual hardware as some of the worker nodes. But this approach has a very fundamental problem. And that problem is the bandwidth that exists between the workers and the parameter servers. So in practice, if you're familiar with computer networking, you've probably recognized that this is the worst case scenario for computer-to-computer communication. So from workers to the parameter servers, you have the many-to-one or many-to-few type of communication. And then you also have another cycle of, one to many back to the worker servers. If you ever looked into how much effort companies like Netflix and other video streaming companies have put into creating this kind of a broadcasting setup to broadcast data to users, in their case, broadcasting videos to users, you know how difficult it is to set up the one-to-many type of a broadcasting environment. So it's inefficient, let's put it this way. So it's inefficient because it's using bandwidth in a way that's not aligned with modern approach to networking. So that's the legacy approach, still used quite a lot, but ultimately, even though it improves on the simple sequential gradient accumulation, it still has many, many problems. So what can you do to do better? And now I'm going to transition to this last part of the session. So we'll probably continue for another 35 minutes or so. And at the end of those 35 minutes, you'll learn about Horovod and this idea of ring-based distributed gradient descent. So just to introduce you to the idea of this ring-style computation, let me set up some data structures and explain how this should work. Notice that I created a constant that has a set of nodes. So why am I using this? Well, notice that I'm taking the number of training examples and dividing this by in-memory shard size. The reason I'm doing this division is to figure out how many nodes I need, assuming that every node can only keep this much training data, training examples in memory, right? So this will ensure that I have enough nodes. And if you're wondering why I'm using floor divide, it's so that I want to make sure nodes is an integer. That's it. So this will divide and then convert to an integer. The gradients that I specified here are completely arbitrary. They're just numbers. What's important for this example is that I have some gradients that are computed on different nodes. So notice that this dictionary basically indicates that, let's say on node 0, I computed the gradient value of 5, node 3 has a gradient value of 1, and so forth. Think of it maybe as a very simple linear regression problem with a single variable, and I'm just computing a gradient of that single variable on different nodes. So with that said, let me give you some intuition behind these ring-based operations. And the first operation that I'll show you is something called O-gather. So this is not Horovod. This is just a part of Horovod for distributed gradient descent. But the reason I'm showing this to you is to get you familiar with the logic of how the communication is done in this ring-based implementation. So if you take a look at this diagram, actually what I'd like to do is start all the way on the right, because this shows you the desired result, the end result of what you'd like to get from this O-gather operation. So notice here, all the way to the right, I have the 4 nodes, just like I had 4 nodes before. And remember that each one of these nodes takes a shard worth of data, the 250 training examples in our case, and then computes a corresponding gradient. So here, for example, node 0 would have gradient 0, which is computed by node 0. And from the simple dictionary, just remember that node 0 computed a value of 5. Again, just as an illustration. What you want to get to with this approach is so that on node 0, you'll actually be able to accumulate all the gradients from all the nodes. Remember, in case of the parameter server-based approach, you were able to do this accumulation on the parameter server. In case of the approach that you'll see here, every node will actually end up with accumulated gradients. So let's take one node at a time and then look at how this would work for node 0. Well, it turns out that if you have 4 nodes, you only need 3 iterations of node-to-node communication. And in general, in this kind of a ring-style operation, if you have X nodes, you need X minus 1 iterations. So what are those iterations? It's a little bit counterintuitive, but in order to get the accumulated gradient on node 0, you actually have to start on immediately the following node, the next node. So notice here that the way that this starts in the first iteration is that the node 1 takes the gradient that it computed from that shard 1 and simply connects to the next node in the ring, right? This is just a logical ring describing how they communicate. And the node 1 sends its gradient to the next node. Then in the next iteration, remember that node 2 had its own gradient, and then it received gradient 1 in the previous iteration. Well, this means that it can accumulate the two together, right? It can add them, or as we call it, reduce in distributed computation. So it can actually accumulate or add them together in this case, and then forward the added result to the next node. So for example, let's say the entire gradient is 400 megabytes. Okay, it's a tensor that takes up 400 megabytes worth of data. Well, every one of these communications would end up being 400 megs. Why? Well, it's because you accumulate the values of those gradients. You take 400 megs here, add it to the 400 megs from the gradient 2, and send the result to the next node. And then in the final iteration, again, you would send the same gradient data, again, the 400 megs worth of gradients based on the gradients added from the previous two iterations to the node 0. And then at the end of iteration 2, node 0 will have accumulated all the gradients that it needs in order to perform a step of gradient descent, which is what this was all about. Now, this is just a simple example to give you a little bit of intuition. This is not Horovod, but let's implement this and see just conceptually how this works, just to prove out to you that this does work, at least in this very simple example of a single node doing the computation. So how do you do that? Well, let's set up the iterations first. So let's do for iter in range. And remember, we only need nodes minus 1 iteration. And the node in this case is going to be iteration plus 1, right? So remember, we're going to start in the next node in this example. And what I'll do is that since we're doing this ring-style computation, I'll do this modular the number of nodes. If you're wondering why I'm doing this modular number of nodes, well, remember when we get to the the iteration that starts getting into node 3, I'll want to do a remainder, and this will ensure that I'll get back and rotate to the next node in the ring, so node 0. So that's the node ID, and what I'd like to be able to do with this node ID is actually figure out the gradient on that node. And remember, the gradient is simply in that dictionary. So it was the node to gradients dictionary. Let's take the value. So the grad variable at this point will contain the gradient value for the node. And next, I need to figure out what the next node is. Well, that's very simple, right? It's simply current node plus 1. I'm referencing them by order. And again, I'll want to use modular nodes so that, when I get to that node 3, this will give me node 0 as the next node in the logical ring. And of course, here, I'm not going to try to provision any worker nodes. I'm not going to try to provision separate virtual servers. I'll make this very simple just to illustrate the concept. And what I'll say is that for this method to work, I'll just simulate communication to the next node. I'll say that the next node in the node to gradients should take the gradient from this node, accumulate it to the next node, right? So no communication, no networking, all of that is swept under the rug, but this is a known problem of how to solve node-to-node communication. So what I really wanted to show you is that if I do this simple kind of an implementation, and assuming I fix my syntax errors, I get back to what I was actually trying to get to. Note that now node 0 has the accumulated gradients from all the other nodes. So if you're feeling like this is too simple, this is disappointing, just remember we're building up to Horovod, which is coming up next. So if you're comfortable with this very simple approach of gather all operation, I can get you started with Horovod, and this should start making a lot of sense. So first of all, what is Horovod? Horovod is a different distributed data parallel approach for training deep learning models. So remember, distributed data parallel means that you shard the data, the training data set examples, into those shards. And each one of the nodes in the distributed environment, those worker nodes, gets its own shard. And it also assumes that all the nodes in your distributed environment processing those shards using identical model parameters or identical models. Okay, so distributed data parallel. The way that this works is that it uses more than just this O-gather phase that I illustrated to you moments ago. It also has a phase known as reduced scatter. And this is something that I'll explain in just a moment. The reason why you need to know about Horovod is it actually is more efficient and it scales better than both parameter server approaches and this plain O-gather approach that I illustrated just moments ago. So when I talk to customers, I find that many of them are actually confused. They think that, hey, as long as I'm using ring-style distributed gradient descent, it's going to be efficient. No, there are some improvements that exist that enables these ring-style distributed gradient descent approaches to scale efficiently to limited memory and limited bandwidth while having effectively arbitrary number of nodes for training. And that's what you'll learn about in the section about Horovod. Now, when I say Horovod, here I specifically mean Horovod, the algorithm. There's also Horovod, the machine learning framework. This is based on the work done at Uber, the ride-sharing company. They originally published Horovod as a paper, but now Horovod is this whole distributed training framework. So I'm not going to cover the entire framework. It's quite heavyweight in my taste. I'll just focus on the algorithm that they described, and you'll see the value of that algorithm, that it's actually fairly straightforward. So that's going to be the focus of this notebook and actually my book as well. And if you're wondering why the odd name, the name Horovod is actually based on this Slavic folk dance. You've probably never seen this before, but if I open this up, you'll see that the dance involves a ring of dancers. And as I understand, they pass these scarves around as part of the dance. So each dancer passes the scarf over to the next one. And I guess the analogy is that these scarves are like gradients in the Horovod example. So we're doing great on time. So let's finish this up. Let's actually work on Horovod. So what's different with Horovod versus other approaches? Remember that before, in that simple ring-style communication, you had to actually transfer the entire gradient from one node in the ring to another node. Think about what that means if you keep adding more and more nodes in your distributed computing cluster, right? Let's say your training data set increases. You'd like to be able to train on more shards worth of data. You try to add 10 times more nodes. Well, that means you're using 10 times more bandwidth at any given point in time because those nodes need to send the entire gradient to each other. What's really cool about Horovod is that as you increase the number of nodes in the ring, you can actually decrease the bandwidth that you need for processing. It actually seems a little bit magical, but it all works, and you'll see that it works surprisingly simply. So, what does Horovod do? In order to support this first phase of Horovod, where you do the reduced scatter, as it's called, you partition the initial shard of data, or actually you partition the initial tensor that you compute, gradient tensor, that you compute based on the shard of data into segments. And by default, you have as many of these logical segments as you have nodes in your Horovod ring. So notice here that I have like segment 0, segment 1, and so on. So these segments are just completely logical chunks or partitions of the entire gradient. So if you take a gradient that's about 400 megabytes in size, think of them as just being 100 megabyte chunks of this entire gradient tensor. And this actually is not that large. So for example, if you're using gradient tensors that are based on 32-bit wide floating point values, 32-bit wide is 4 bytes. So this means that you here, if you have 100 million parameters in your deep neural network, you're already going to have a gradient tensor with 400 megs. And today, if you look at cutting-edge deep learning models, they're easily in hundreds of billions of parameters. So significantly larger than what you're looking at here. So it's very important to be able to divide these gradient tensors into smaller segments, as you can see here. And the surprising thing about these segments and the way that Horovod actually works is that if you think about these segments, you cannot add them horizontally. So in other words, you cannot add segment 0 from node 0 to segment 1 from node 1 and so forth, because then you lose the original gradient, right? You can't just compress this down, the 400 megs worth of gradient, to 100 megs by adding them horizontally, right? Adding them like this. If you prefer pandas terminology, you cannot add along axis 1 and get a meaningful result. But think about adding vertically, okay? So if you were to add these vertically, you'd be adding up the segment 0 from the first shard, right? This shard 0 to segment 0 for the next shard and so forth. And what would you get back are these accumulated shards. I'm showing them right here. And these accumulated segments would represent the accumulated gradient from all the individual nodes that you have here. So that's what I'm trying to represent. The idea is that you can add them vertically, as shown here. So with that in mind, let's actually go ahead and figure out how would this work. And again, I'll simulate this implementation. And here, instead of just having a single model, remember what we want to have is a list of models. So in fact, I'll create a list of tensors. Each one of those tensors is going to be based on those same NumPy values I had moments before. Remember that each one would want to have requires grad true. Each one would want to have the data type be, in our case, float 64. Float 64. And let's actually take a look at the result. So here I have the tensors, and actually let's do this for in range nodes, because I want to have as many of these different W models as I have nodes. So now I have this list of different independent models, and this is going to represent the independent models, those independent model parameters that you have on each node in the Horovod cluster. So now let's actually perform a single forward pass of gradient descent for every node. And an easy way to simulate this is that I want to have a node, right? And I can have a node in range nodes, right? I want to perform a forward pass of gradient descent on each one of these nodes. But what I'd like to do is actually make sure that for every node, I also have its own shard of data. So Y shard and X shard worth of data. So how can I do this? Well, I can simply zip up the range of nodes together with the training data loader. And this will make sure that for every node, I have a separate shard of the training data examples. And now the rest is just like before. You estimate the values. So let's do a forward pass where you specify a forward pass using the model that exists in that corresponding node and the corresponding shard worth of data. Now, if you're wondering why I'm using the values that are specific to the node here, since they're initially all the same and they have to be the same, the reason is that the gradients actually are going to be different, and I'll show you that in just a moment. So let's actually go ahead and compute the loss. So just like before, the loss is mean squared error of the estimated values and the target values from that shard. And now I can do the backpropagation of the gradients. And since the data is actually different for each one of these nodes, right? Each shard is specific to the node. The gradients are going to be different as well. And that's really what I'm after. So I'm going to compute the gradients. And what I'd like to do next is actually output those gradients that I get back after the computation for each node. So let's do this forward pass and then backward pass of gradient descent. And to output the gradients, let me output a list of gradients using formatted strings. So the way I can do this is have a formatted strings for every node, right? This will give me access to the gradient values for every node. For node in range nodes. Let's go ahead and run this. And now notice that every node has its own gradients, which is not surprising because every node has its own chart. Now, what you can do, however, is actually figure out what the aggregated or summed up gradient should be. So let's set that up as the target for Horovod, what it should compute for us. So let's do it by computing the sum of W node gradients. So the gradient should be here for node in range nodes. And this is the this looks similar to what the gradient should be, but actually it's not. And I'll tell you why. It's because I just introduced a bug into my code right here. And if you look closely, you get bonus points for actually identifying the bug. I'm checking in the Manning chat. Doesn't look like anyone actually spotted the bug, but I did have a bug in this code. So the bug is that, remember, I have to do the rescaling. So this should be in-memory shard size divided by training dataset size times the loss function. And if you forget why do I have to do this? This is to make sure that the mean squared error that I'm computing is measured in per training dataset example as opposed to in-memory shard size. So let's rerun this. Let's actually make sure that I take the original data values for the parameters, rerun it. So let's do a single pass iteration of gradient descent, review the updated gradients. So this looks better, and look at the sum of these gradients. And this is what I want you to notice and remember right now. So these are the gradients that Horovod should actually be able to compute using the reduced scatter and the next approach that I'm about to show you. So what is this reduced scatter? Actually, it's quite simple if you take a look at this animation. So let me pause this just for a moment, and I'll explain what's going on in this animation. So remember that when you started by passing in a shard worth of data into every node in this logical ring, and every node computed the gradient and partitioned those gradients logically into these segments. So in this reduce scatter operation, you also have independent iterations of compute. And in every iteration, instead of passing in the entire gradient from one node to another, you only pass a fraction of the gradient. In fact, you only pass a single segment to the next node. Surprisingly, this will actually help you recover the entire gradient into two phases, and this will limit the amount of bandwidth you actually need. So how does this work? So notice that in this initial iteration, every node takes a segment and passes it to the next node in the ring. So in fact, node 0 takes the last segment and passes that to the following node. Node 1 takes the 0th segment, passes it into the following node. Node 2 takes the first segment, passes into the next node, etc. So I can actually let this iteration continue running. So let me do that. But basically, that's what's going on. Notice that after the iterations, you'll have more of these segments on every node. And at every iteration, it is the reduced or accumulated segments that get passed forward. So this indicates that you're simply adding up these segments, and then the added up segment is sent forward. And remember, the segments themselves actually only consist of a fraction of the data needed for the entire gradient. So in our example, the gradient was 400 megs. Every segment is 100 megs. And remember, you can add vertically. So this sum of the segment also ends up being 100 megs. So when you're passing in the segment 2, which is based on the accumulation of segments from node 0, node 1, node 3, this gets forward to the next node. And at the end of the last iteration, so remember, 4 nodes per iterations, in general, x nodes, x minus 1 iterations. At the end of all those iterations, every node will have one reduced segment worth of the gradient. And this is what's indicated right here. So node 0 will have segment 0, node 1 will have the entire segment 1, and so forth. So it's almost like you're very, very close to getting to being able to do the reduce reduce all operation, share those segments like I did in the simple example, and then recover the entire gradients on all of these nodes while only communicating one segment worth of data at a time. So the implementation of this first phase of Horovod, reduce scatter, is again surprisingly simple. You still have to do iterations. So let's do for iter in range. Let's do nodes -1, right? One less iterations. But now let's go ahead and do for every node in range nodes, so we can actually do the reduce scatter. So now the node is the current node in this phase, and let's recover the segment that that node should process. And that segment ID, or the segment that you should be working with, is in this case should be the segment corresponding to the current node minus the iteration. So remember, node 0 at the beginning of these loops, iteration 0, and that node 0 should send the last segment from the list. So it should send segment 3. So that's why here this will be -1. And if I do modular nodes, this will give me the last segment out of the gradient, which is segment index 3. So this is the idea of the segment. Let's actually figure out the gradients themselves. And the gradients are easy. They're just w node dot gradient, and then segment within that gradient. And now you can see why I've been using 4 features in the multivariate linear regression, so that the number of features and the number of segments corresponds to the number of nodes. So this recovers the gradient segment values that you want to send to the next node in the ring. What is that next node? Well, that's trivial. It's just the current node plus 1, right? The next node, modular nodes. That's the next node. And now let's go ahead and accumulate these gradients as you do in reduce scatter. So this means that for the W next node gradient segment, you want to accumulate the value of the gradient from this node. So here, again, I'm simulating sending of the gradients from the current node to the next node into the same position. So let me go ahead and run this. And let's confirm that this works as expected. So again, let's output a formatted string that contains the gradient segments for every node. So this would be W node dot gradient. Let's close this, close the string, and this would be 4 node in range nodes. And let's see what this comes back with. And immediately, if you remember the gradient values, notice that this gives you the expected result. Remember, the 0th node has the correct gradient in the 0th position. The node 1 has the correct gradient in the 1 position, and so forth. And in fact, already, if I do the following, let me just copy and paste this in the interest of time. Let's do it this way. The gradients that were just reduced scattered over the ring actually are the correct gradients. So the node has the correct gradient in the corresponding segment, as you would expect right here. So node 0 has the correct segment gradient right here, node 1 correct segment gradient here, and so forth. And in fact, as you remember, this is the target, so the values are exactly as you would expect after the reduced scatter. Well, now that you have the reduced scatter, let's just forward these results to all the nodes, and you'll end up with the accumulated gradients. So remember, at the beginning, you had the correct segment here. So in the first iteration, it got forwarded to this node. Next, in the second iteration, you'll forward the next gradient that was just sent over. Node 0 received the segment 2, so let's go ahead and forward it to the next node. So we fill that in. And after these 3 iterations, remember 4 nodes, 3 iterations, altogether is done. Let me put a pause on this animation right here. There we go. And that's all that you're after. So simply by communicating 3 iterations worth of segment data from one node to the next at a time, you end up what you're really after, which is the accumulated gradients on each and every one of the nodes. So let's go ahead and actually wrap this up in this last part of the Horovod implementation. So let's do for iteration in range nodes minus 1, for node in range nodes. So let's go ahead and figure out the segment. So in this case, the segment is simply going to be node minus iteration mod nodes. And the value of the gradients in that segment are simply W node that was computed, and then gradient segment. So these are the gradient segments, node minus iteration. This makes sure that the node 0 in the first iteration communicates the gradient segment from segment 0, which is what you're after. And next, let's send that segment to the next node. Next node is just node plus 1, mod nodes. Let's go ahead and simulate sending of the segment. Notice that now it's not accumulating the segment, it's actually updating it in the next node. So grad segment is equal to grad, and that's it. So this basically updates the segment in the next node using the current node segment value. And at this time, if you actually go ahead and output the gradients on each node, so let's do W node grad for node in range nodes. This is this is close to what we're after. So as soon as I fix this bug that I introduced here, so I did the node minus iterations, I've updated this. So node plus 1 grads equals grad. And W node, next node. This is the bug right here. After I run this update, all the gradients are distributed correctly to every node in the logical ring, which means that these gradients have been collected from all the independent workers using limited amount of bandwidth, using limited amount of memory, and ultimately at the end you can bring this all together into a full-featured gradient descent using 2 phases of Horovod, of reduce scatter and all gather. So this is just the same exact code I showed you moments ago, put together into 400 epochs worth of training using initial values from W numpy like you've seen before. And let's go ahead and let this run and see what it comes back with. So right now, after 400 megs worth of 400 epochs worth of training, you can see that you get exactly the same results for the coefficients as before. You recover the coefficients with those interesting values that I pointed out. So if you're wondering, will this actually completely recover the gradients? Yes, absolutely. You can just run this again with the same model. You'll get the gradients back. So let's do this, run this again, and this recovers the coefficients correctly. And in a nutshell, what just happened? Notice that in just let's see, less than 35 lines of code, you've implemented gradient descent that can handle out-of-memory data. It can handle limited bandwidth, scales well with increased number of nodes over the network, and gives you ordinary gradient descent over the entire training data set. And if you're interested in the book, I also talk about how to adapt this so you can process a batch worth of data as opposed to the entire training data set at once. So if you're interested in doing mini batch gradient descent in this kind of a ring style communication, you can learn more about that in the book. With that said, I hope this was interesting. I wanted to say a huge thank you to all of you for participating. Again, remind you that you can get access to the book if you follow the bit.ly link in the upper right hand corner, and also on the lower right hand corner you can see a discount code that you can use to get 40% off of the list price of the ebook version of the book. So if you're interested in scaling up your machine learning systems, putting them in production, definitely check out the book. For everybody else, I wanted to say thank you for your attention. Feel free to reach out to me using the information that I shared in the beginning of this session. And I'm looking forward to continuing the conversation with you. Thank you all so much.